My name is Yannick Tremollet. I'm the JEDI project lead, and I'm going to give a little bit more explanations about data assimilation algorithms in JEDI and OOPS, just to complement what Anna has just presented. So this is not a data assimilation training course, but I just want to give you a 2-minute reminder about some of the data assimilation concepts. So you all probably know that NWP is a cycling process where we repeat a forecast typically every 6 hours for global models, and more frequently for local models, can be 1 hour or even shorter. And the period over which we use observations called the assimilation window. So that's typically like the last 6 hours for a global forecast, let's say. And this process of repeating the assimilation and forecast is called cycling. So just to be a little bit clearer about the scope, the cycling algorithm is actually coded in scripts and in workflows. And that might include hundreds or even thousands of tasks per cycle that have to run on HPC systems. And the data assimilation itself, whether it's ensemble or variational, is happening in one of a few executables. And what we're currently developing tools for doing the cycling that are well suited for JEDI, but that's in development. And the release, the current release of JEDI AV3 does not include all the tools for the cycling, and this academy is the same, and it only covers what's in the data assimilation algorithm, the codes for doing the data assimilation and the YAMLs and etc. to configure it, but we do not include all the cycling here. So just a reminder of what an assimilation window is. Typically, you have some previous forecast, some period of time over which you have observations, and we call that the assimilation window. As I said, typically it's 6 hours for global forecast, although some centers use 12 hours. And for regional forecast, it's going to be shorter. Typically for ocean application, it can be something like 5 days for your assimilation windows, typically. So we have this previous forecast, we have these observations. The idea in a 4D assimilation system is you compute the difference between the observations and the forecast, and you try to minimize that difference. You try to find the initial condition for your forecast that are going to make that difference as small as possible. So it's an optimization problem where you try to find the initial condition for your forecast. Now, a 3D assimilation window is you start from the same point. You have your assimilation window, your forecast, your observations. But what you do is that you only consider the forecast in the middle of a window, and you bring all the observations, you neglect the time difference, and you bring everything at the time at the center of the window, and you do your assimilation that way. It's a lot cheaper because you don't have to run the model back and forth in the assimilation window. But it's also, of course, an approximation, and it's not used anymore in operational systems, as far as I know, at least for the atmosphere. It's still used for some of our applications. And you get your analysis as a kind of a weighted average, if you want, of your background and your observations. Now, what is still used is what's called 3D FGAT, so it stands for first guess at appropriate time, where you start from your forecast and your observations, and you compute the difference, where you take the time into account when you compute your difference between your forecast and your observations, and then you only consider the time at the center, and you consider that your forecast is constant over that time window, move all the differences around that, and you do your assimilation. So it's only this time, it's still an approximation that makes the process cheaper, but the initial input, the departure, the innovations are computed correctly, taking the time into account, and it's only than the optimization process that neglects the time dimension. So that is still used in some places. So just to go back a little bit into the analysis and design that led to OOPS the way it is now. So this is something that, just what I've said before, data assimilation aims at estimating the set of a system given a previous forecast, some observations, and possibly some other constraints with like theoretical information like balance constraints and a few other things that you might want to include. So I've just written down an example here for variational data assimilation, and you could add extra constraints to that cost function if you want. So the way we do that in JEDI, the first question that really, when we started this whole project many years ago at ECNWF, was how do we design the system and how do we design the cost function, because that was the kind of the heart of all the variational DA. So one easy but fairly simple approach is that you create one object for each term of the cost function. So typically, the JB, the JO that you have in your cost function. And then you can compute each term or its gradient when you need it and add them together, and that gives you your full cost function. Now, the problem with that is that the model, you will need to run the model several times because it's needed in the JO term, it's needed in the JC term if you want. If your JC is a digital filter, for example, you need the model. JQ here would be a model error term, which also involves running the model. So you would run your model several times, and that's not something you can do because, the model is, in a 4D system, at least the cost of running the model is more than 90% of the total cost of the assimilation, so you don't want to do it several times. So there's another approach which you can do, which is to run your model once and store the full 4-dimensional state. And then from that full 4D state, you can compute all your terms of a cost function, add them together, or same thing with a gradient, etc., and do your assimilation. Now, well, as you have called it a naive approach, so it doesn't work. The problem there is that the full 4-dimensional state is way too big. It doesn't fit in any HPC systems that exist around the world at the moment, but orders of magnitude larger if you really want to do it with that approximation. So that doesn't work. So the only approach left really is that you want to run the model only once, but you want to compute the costs, the terms of a cost function as you go, as the model is running, and then you add all the terms together at the end. And that's the only way that you can actually compute everything with that approximation, and at the same time that it would fit in memory and doesn't cost too much in computing time. So that's how OOPS was designed. So we still have a class for each term of a cost function that gives us a lot of flexibility in how to define the cost function and add some new terms if we want. But we also have a way to call these terms of a cost function as the model is running on the fly. So for that, we use a post-processor structure. And the idea is that each term of a cost function corresponds to a post-processor, which I will explain a little bit more. And this post-processor is being called while the model is running. And at the end, the output of this post-processing step is passed back to each term of a cost function, and you can compute your cost function. Saving the linearization trajectory for a tangent linear and adjoint model, if you're doing 4D VAR, is also a post-processor that follows exactly the same structure, which is nice. So we have only one post-processor structure for everything. just if you look at the code really in detail, you will see that there is an abstract cost function base class, and then there's several subclasses. There's one for 3D var, one for 4D var, one for weak constraint 4D var, one for 4D EN var. You could actually, if you're really clever in how you configure it, do everything with the weak constraint 4D var cost function. The other ones are just special cases, but it was these classes have been kept just so that they're a bit easier to read. And for people who want to get into the system, I would advise you to start with the 3D var, it's the easiest one to read, and then go to 4D var, and then to the other ones that are a bit more complicated to read. Now, in terms of the efficiency of that reusing of the terms of the cost function, the 4D EN var was added to the system in one afternoon, basically. So it didn't solve all the scientific question, but all the technical work was done in one afternoon. And then, then you can start looking into science and decide what localization you want, and etc. But compared to the system that existed at DCMWF at the time, the AFS, it would have taken months of work to put a 4D EN var in the AFS. So that was definitely a big success. So just a little bit more about post-processors. So post-processors are called during the model integration. One key point here is that the presence or not of post-processing should not and does not affect the forecast. So whether you do post-processing or not, your forecast is going to stay exactly the same, which means that the post-processors, they take the state of the model as an input that's const, so you cannot modify the input. That's pretty much the only constraint about post-processors. You can do everything you want other than modify the state. And post-processors really isolate the model code from many unrelated aspects, so that's really a separation of concerns. And we think it would be good for most existing models should actually move into that direction more and really have a model code, which is something that model scientists can work on. And all the I/O, all the, if you want to, operational centers might want to generate products on the fly, and various other things you might want to do. They should be done by post-processors. There's absolutely no reason that should be entangled with the model code. So even though OOPS stops at that level, you could go with the separation of concern approach much deeper into the models. Now that's not the way they're written, because model codes are usually fairly old codes, even sometimes very old codes, and they are not written using modern programming techniques, but they would really benefit a lot from doing that if they wanted to. So some examples of post-processing, as I said, output of forecast fields, generation of projects, computation of filtered states, so that's for digital filter initialization, trajectory for linearized models, simulated observations, that's what we use a lot. That's the most important point for data simulation, is the simulation of observations. Diagnostics, and you could actually use that simulation of observations during a forecast just to simulate future observations and ahead of time and do some kind of diagnostics from that. So there's all kinds of interesting things you can do with post-processors, and I'm sure people will add more post-processors. More post-processors. So I'm having trouble changing slide. So this is an example here of what a YAML file for 4D var looks like. And I've put with this dollar parenthesis, these are actually longer sections of YAML that I've kind of removed here for readability of this slide. So you see that it defines a cost function, which is a type here for the var, window begin and window length, and then it has things for the model, so the geometry, which is basically, you can think of that as a definition of your model grid, your resolution, etc. distribution across processors, then your model, define the analysis variables, your background error observations, and then the variational data assimilation itself, which is going to have a minimizer. We have a collection of, I think it's about a dozen different minimizers, and you can define a number of iterations you want to do, the criteria for stopping the minimization, and typically the minimizations are done on different geometry, a different resolution to go faster. So you have a second geometry here, which is going to be a lower resolution than your full model that you use to compute the innovations. So this is just showing you the high-level structure of the YAML. Each of these sections where I've put this dollar parenthesis here is actually itself a whole section of YAML, but I think it's easier to see that way what the high-level structure is. And this is actually the way we are writing this YAML as a template for the tools that are going to do the cycling. So we'll have a high-level 40var YAML like that, for example, if you want to do 40var, and then these tools that go around JEDI will replace the geometry and model sections by whatever is relevant for your particular model that you're running with. So there'll be again a separation of concern between what's the high-level YAML that's for 40var and what's specific to your model that you want to include in there. Going to 3dvar is actually fairly easy when if you have a 40var, you change the type of the construction from 40var to 3dvar, and you can remove the model and linear model sections, and that's it. Everything else stays the same, and that's how these things are very related, so they should be similar. And if these YAMLs are a bit intimidating, looking at them in this way, just looking at the high-level structure really helps to understand what you're doing. And if you want to do a 3D FGAT, again, this time you leave the model, so you still use the 40var cost function. We didn't write an FGAT specific cost function. You still leave the model in there for the computation of the innovations, but then the linear model is actually replaced by an identity model, which is just a model that does nothing. It's just immediately returned. You call it with an increment, it immediately returns and does nothing. So that makes it a lot faster. It also means you don't need to have a tangent linear adjoint model if you don't want to. This identity model is actually generic. And the time step we needed for, because it's the code's looking for it, but it's not actually used for anything. So that's how you could change from 3dvar to 40var to 3D FGAT if you want, just fairly simply by editing your YAML. Another comment I wanted to make about the YAML, I know these YAML files can be big and can be intimidating. Some editors will let you fold and unfold the YAML section. So here, for example, on the left, I'm using here Atom as an editor, but other editors do that too. And it's putting here this little greater than sign here on the left, where and this sign on the right, where it's a section that you can open. And here, for example, for background error, it's a section that's closed, and I can click on this arrow on the left, and it will open that section and show me what's inside. So yeah, it's fairly simple because it's a Lorentz model, but it could be more complicated. But if you look at it, the way that it is on the left, you see that it collapses the YAML and it makes it a lot easier to read. And you can just open the section as you want to work on it. And it's also much easier to see if your different sections are indented properly, because the indentation here is fairly easy to see. So it helps a lot to have an editor that can do that if you're going to work with these YAML files. All right, and I'm going to go into the application. So it's something Anna has mentioned a little bit, and I'm just going to give a few more details here. So the applications are found in this source oops runs directory. So I've just listed a few here: variational.h, forecast, h of x. There's, I don't know, there's like 15 or 20 different applications now. Applications, they are the normal way to run JEDI. That's how you should run, 99% of the time. Unit tests are very special applications. So when you run your C test, it's actually running these unit test applications that are kind of hidden from the user. I mean, they are there somewhere, you can find them, but you don't really need to go into them. And their unit tests are applications that just run tests for a given class at a time. So you would have one unit test for the state class that's going to run tests that are going to check that your state class is doing what it's supposed to. Same thing if you think about your covariance matrix or your increment. It's going to verify, for example, for your increment, it's going to do some checks that the linear algebra is functioning correctly. Things like that. Now that's also something that typically in old style codes, because everything is global variables and it's all entangled, you can't really do tests of specific parts of the code independently of the rest. But that's another advantage of a separation of concern, is that because we've isolated the code in self-contained units that are called classes or objects, we can now test them independently, and that really makes your development easier. And people were talking earlier about adding a new model. Typically, what you would start by implementing is your geometry class. It doesn't have many tests for that one because it's a very simple class that basically holds a few definitions. But then you define your state class, and you can start testing that it's going to read and write a state. And a few other things, and then you start writing your increment class, and you can start testing that your linear algebra is working. Obviously, if your linear algebra is not working and you cannot do a dot product between two increments correctly, there is no point trying to go further. You know already you have a problem, and you start fixing it in a simple framework before you go further. So these unit tests are very, very important, and you will hear more about that. I forgot if it's tomorrow or Friday, but you will hear more about these unit tests. Variational applications, I've talked about that. So that's really the heart. So that's how OOPS started, and I think OOPS has all the variational DA methods I know of, including observation space and etc. They're all in there. There's a whole range of minimizers that you can try in primal and dual space in this double primal space. So this Derby-Rosati algorithm, that's what's done in the GSI as well. So that also is there in OOPS and JEDI. And there's also a saddle point algorithm for the weak constraint. I wouldn't recommend using the saddle point for other problems, and weak constraint is not really designed for that. And then there's several algorithms in each of these spaces. So there's a whole collection of things you can do there if you're interested. And it's all controlled from the YAML file just by changing this minimizer line. There's several preconditioners as well. Just a few words about ensemble applications. So this source OOPS runs also contains this application that's called ensemble application. That's for running ensemble applications, as the name says. So ensemble application is a very simple class. It's templated on an application. You've heard about templates earlier today. So, and you can pass as a template argument there, you can pass the variational of the forecast or the h of x or any of the other applications you want, and it will run an ensemble of these applications. So it's very simple. I think it's about 77 lines of C++. Hopefully that hasn't changed since then, but it's a fairly short way of being able to run an ensemble of applications in one executable. Now, that can be convenient. You don't necessarily want to run all your ensemble members as one executable. It really depends on the context. Typically, operational centers prefer to run them as separate executables because it's easier to manage in the queues, and it's easier if one fails to rerun just that one. But there are contexts where you might want to run it as one application. So, and you just give it a list of YAML files, basically one for each member in your ensemble, and it will run like that. Now, the fact that it's taking a separate file, this list of files, means that you can easily run one member by just giving it exactly the same YAML file as a separate application. So it's very easy to swap from one to the other. So yeah, I'm just going to stop here for the ensemble application. It's just good to know that it exists. So there are more applications. I've listed a few more here. I think there's even more than that now. I forgot to update this slide yesterday, but there's quite a few. And the collection we keep adding more applications as we go. So I think there is, most of the applications that you would need to run the equivalent of an operational global systems are there, but there's probably going to be a few more for research in the future. Not all of them are fully documented, so feel free to explore. And if you like documentation, then please start writing one. That would be, I think everybody will like you for writing these documentations. If you want to contribute, that's a really good way when you start something to contribute to the documentation. It's a really good way to learn. And you also get a better view of what somebody who is new to the system needs in terms of documentation. Obviously, for some of us, some of these things are obvious, and we don't necessarily feel that they need it in the documentation. But for a newcomer, they might be needed, and it's always good to have people kind of contribute in that way. So I think this is just a recap of things we've said before. You just need, given all these JEDI applications are generic, and you just need to change the YAML file and your template argument when you're compiling to change the model. You don't need to recode anything. Once a model is in there, you can swap without any coding. And you can do a lot of developments with the toy models for testing a new data simulation algorithm. For example, you can test it with a Lorentz model and a QG model, and then go to your full model. And there is no coding needed to swap from one model to the next. So even in an operational center, when you want to develop something new, it will save you a lot of time to first test it with a Lorentz model before you go to a more complicated model. Debugging is a lot easier. It runs on a laptop. It's super quick. So that's always extremely useful. And the last comment I want to make here, if you feel a bit lost in the code, a really good way to learn is to run the code in an interactive debugger. That's really a very educative way of running the code. You don't want to do that all the time, and you might not want to do that with a model at operational resolution. But if you have a very low resolution case with your model, that's a very nice way to learn.